All right. Good afternoon, everyone. Let's get started with today's class. So I just published the grades for the midterm exam. Let me know if you don't see it. But also, so you should be able to see both your grade and I would imagine the feedback that you received in each one of the questions that you missed. If for some reason you cannot see either your grade or the feedback, let me know. And also, we're not going to be talking about the exam specifically in class, but if any of you have any questions, perhaps you think that you got something right and I gave you a wrong answer, whatever it is, please feel free to let me know. I can make mistakes as well, and so if there's something that you think I graded wrongly, I'm always open to talk about it and reassess. And if indeed I made a mistake, I'm glad to fix it. But I did try to not make any mistakes. So yeah. So anyways, whenever you can take a look at your exam and the grade you got and the feedback you got. And if something doesn't make sense, or maybe have a question about, an answer that I was expecting, let me know. We can talk about it. Yeah. You're not able to see the feedback? Okay, so Amandeep telling me that you cannot see the feedback, just the grade. Can you see the like which questions you got right and which you got wrong? No? Okay.
It's the same for me too.
Is that the same for you, Kathy?
Yeah.
Oh, yeah, let me see if I can, later after this class, I'll get together with Amandeep here and see if I can figure out a way for you to see the feedback as well. Um,
Sorry, also, I'm not able to see the grade or the feedback.
oh, you're not able to see the grade, Luke?
Yeah.
Okay, huh, okay.
On my side, I can see the grades and the feedback. If you go to the tools and you select quizzes, and on that option you can see the comments.
Okay, so if Polly can see it, at least, well, so I guess I did, so Luke, you're in a different,
Actually, I do see it now. Sorry, yeah, it's there.
perfect. Can you see that, Aman, as well?
Yeah.
Okay, all right, so you can see the grade you got for each question, and if there is a feedback, you can see the feedback as well?
Yeah.
Okay, perfect. All right, okay, so yeah, once, I mean, it is probably not gonna be today in class, but after class, take a look at the feedback you got, and if you have any questions or issues, let me know. We can reach out to me by email, we can have a chat and go over any questions you may have. And if I see a pattern, like let's say if for some reason I graded something wrongly for everyone, then I'll bring that up in class if it's something that applies to everyone. I hope that's not the case because I try to grade fairly and correctly across the board. But anyways, if I realize there is a pattern that everyone is asking to revise a specific question, then I'll bring that up in class and we can discuss about it. But otherwise, if you do have any questions or concerns, let me know by email and I'll be glad to connect with you on a one-to-one basis and we can go over it. All right, so we are going to continue and most likely finish our terrain exercise today. So if you go to the class folder, we were working with the 08 terrain project. That's what we were doing. Remember, I always ask you to launch the rproj and not the script. So launch the project that we have here, and that should bring up all the files related to this project specifically. And I think we stopped right here when we created the grid, right? So maybe what we can do is we can just go to the beginning of this exercise and kind of walk through quickly what we already did so you all get a reminder of the steps. So this exercise here, we're basically working with terrain data. And on terrain data, the main variable, the primary variable that we work with is elevation. And then we use that primary variable of elevation to calculate secondary variables. So if you just make sure you run the chunks, so we start creating the objects here. So I just loaded all the packages, created that my theme, and then make sure you bring this object, this 08 elevation CSV. We're assigning that to this object called elev. And here is basically elevation data. We have about 55,000 points of elevation across our field. And even though it may not look like, but these are all points. So they were collected as points, and we need to interpolate those points at in a given part of this exercise. So, I hope that now that you've seen the types of questions I ask, you may be able to relate when I ask these questions in class, and you can think of, okay, that's probably a good question for an exam that he'll ask, because I keep asking you some of the many same questions every time. So, again, we bring this, it is a CSV file. This file is not geospatial, right? It is just a CSV, but it is a geospatial layer. And we know that because we have coordinates of X and Y. This question here on the exam, I was actually grading this both ways. If you said it was geospatial or you said it was not, I was taking that into account as long as you explain why you thought that was. So if you told me it's not geospatial because it does not have a geometry, you got it right. If you told me it is geospatial because it has a point X and point Y columns, you got it right as well. So just so you have some feedback on the questions. But anyways, it is CSV, so it's not a geospatial file, but it is a geospatial layer because it has those columns, right? So we're doing these very common wrangling steps that we do a lot of times. So doing clean names, we're renaming elevation and including the unit to make this more informative of a column name. We're then creating elevation meters, just selecting elevation meters and then the coordinates, transforming this to an SF object using ST as SF, setting the native CRS using ST set CRS, and then transforming to our projected CRS. So there was a couple questions related to these. Make sure that if you did not get that right, make sure that you do understand why you got it wrong and what was the correct answer, because these questions may come back at some point. So just keep that in mind. All right, make sure you run that. So now we end up with a SF object of type point, still with the same number of rows, over 55,000 rows. We made a quick plot here by sampling 50% of the data and plotting it, just so we could see it's actually a point shape file. And you may think of like, okay, there's so many points here. I know that at some point, if you start zooming in, you're going to see the space between points. But do we really need to interpolate this? It just seems like such a dense layer. So the reason why we are interpolating is because first we want to have this layer as a raster, right? So right now it's vector. It is a point vector layer. We want this as a raster. And when we do interpolation, if you remember, the way that we interpolate is we need to have the point that we're interpolating, the point layer we're interpolating, and the grid. So we're interpolating those points over this grid and using the grid. And so each grid cell is going to get a prediction of, in this case, elevation. The key thing here is that we want to have that same grid for everything we do in this field. So if you remember, we already did interpolation for yield, so using the same grid. Now we're going to keep doing that for every layer that is point like this. So we continue to use the same grid in a way that when we bring all these layers together, they're going to all have the same grid So all the cells are going to line up perfectly between soil properties, soil electroconductivity, EO data, and so on. All right, so to do interpolation, again, regardless of what type of interpolation method we're talking about, to do interpolation, you have to have a grid. For us to create a grid, we always start that off with the boundary. So the boundary is our cookie cutter for where the grid is gonna be located within that boundary. So that is our initial step, is to bring in a boundary and then use that to create a grid. So here we start off with the boundary. We make cells of size 10, and this 10 here is meters because boundary is in UTM and AD83 in meters, it's projected. Then we rasterize and crop to the boundary, so make sure you run that. And then we made a quick plot here. So although it's not very clear to see, but we have cells here that are in 10 by 10 meter size, and that is the grid that we've been using to interpolate. Okay, I think we actually stopped right here. So we stopped at the point where we created the grid and we were ready to interpolate our elevation data. So let's go ahead and do that. So this was a question in the exam. And if you go back to the recordings, a few times I said, for us to interpolate, there are two steps here. Let me close my email so it doesn't beep. I said there are two steps here. The first one, we set the formula that we're interpolating. The second step is we predict based on the grid. So that's what we're going to do here. So let's see if anyone, I know some of you got the question, or most of you perhaps got the question right. So what is the function that we need here to do the first step of this interpolation process? Anyone remembers that? All right, so I'll help you out. It is gstat. There's a function called gstat from the package that has the same name, where it has an argument for formula. So here we're basically going to say, what is the variable we want to interpolate? The name of that column is 11_meters, and you just give a tilde1. This is what the formula needs. You're just saying that you want to interpolate the column elevation. And then it has a data argument. So data equals our object, which is called 11_w. If I print 11w, you're going to see there is that 11 meter column right there. That's the one that we're interpolating. So if you run this and you print IDW mod, this is just setting up the model, setting up the formula that we're going to be using to interpolate. It has not done interpolation yet. That is going to come in the next step.
Dr. Bastos,
Yes.
can you please scroll up to the previous chunk? I think I missed something.
So everything.
No, the previous one. It says object grid are not found for me.
Okay, maybe you didn't run this. So we already did this coding
Yeah.
in previous class. So maybe you just forgot to run.
No, I did run, but I forgot to put the brackets around. Yeah, I just made a mistake. Thank you.
Okay, yep, no problem. All right, so gstat, we basically just
It's
set up.
object not found.
Sorry, what's that?
It still shows object not found.
So what object is not found?
Grid R.
So we're not using grid R yet in this chunk. So I wonder if you have.
Not that. The previous one. The previous. Yeah, there.
So what happens when you run this?
It says grid are not, object grid are not found.
I'm not sure what is going on. So if you highlight this and run it,
Mhm.
creating grid R, right? So it's not looking for me.
Okay. Can I send a screenshot with the? I don't know.
Uh,
The channel is not running.
can you send that on GitHub and then Neva can help you out?
Yeah, thank you.
Yeah, and then so Neva, can you take a look at GitHub? Kiati is gonna post there. But yeah, I'm not sure, Kiati. It may be that you're missing. You may be missing like either a pipe or maybe a closing parentheses. Something you may be missing in your code.
Yeah,
Yeah, but Neva's gonna try to help you out and
thank you.
thanks. All right. So we first established here on GStat. Kathy, I'm going to put you on mute just because I'm hearing some echo. But if you need to speak up, feel free to unmute your-
Sorry.
No problem. Okay. So first step here, GStat. This is where we establish where is the data frame that we have the point data and what column we want to interpolate. This is what happens at this level. And then on the next level is when we predict. So we're going to predict those points over our grid. So here, if you come on the next chunk, we're going to use the function predict. So here we give two objects. The first one is this model that we just created above. So IDW mod. And then we give the grid, which is called grid_r. So if you run this, this is actually where the interpolation is happening. This is where it's truly happening. And just as a reminder, the interpolation method that we're using is inverse distance weighted because it takes the inverse of the distance as the weight for the point or for the cell that you are interpolating at a given point. Now, if we print IDW pred, this is a stars object. And if you remember, stars object is raster. So every time you do interpolation, the immediate product out of interpolation is going to be a raster. At some points in this exercise, we're going to transform this raster stars into vector SF just as an option that I'm having because I think it's a little bit easier for us to visualize the data all together when we get to that point, which we have not yet. But it's an option that I took by design, but we could have worked with them as raster if we wanted to. All right, so we just interpolated elevation. Now, and every time you do something happens behind a function, you need to inspect your results. Do not just assume that everything worked fine. You have to inspect your results. So a good way of inspecting geospatial data is to plot. So we're going to create a plot here, and we're going to assign that plot to an object because I want to bring this object back in the end when we merge a few different plots. So if we want to do a plot here that I want to show the elevation data that we just created above. I left you the object, I left you the ggplot, and we want to plot the output of this IDW pred. What geom do we need here? Okay, Amandeep said geom stars, and that's correct. How we know that is because this object that we're plotting is a object of type stars. So geom_stars, we need to say data equals to, and then the data set name, which is IDW_pred. If we just run this and print it, this is how it looks like. If you remember, geom stars does not shape our field the way that it should be shaped because it tries to optimize both X and Y axis. And so it kind of squeezes or elongates things in ways that should not happen. We can fix that in a couple ways. One could be to use the chords equal function here in ggplot. But another solution is to bring a geom_SF because for some reason, geom_SF does plot correctly with the dimensions of X and Y. and GeomeStars does not. So let's go ahead and bring here our boundary. We're going to use GeomeSF for that because the boundary is an SF object. We're going to say data equals boundary W. That's our object name. And let's say fill equals NA. So our bound, we can see through our boundaries, not blocking the data behind it. So if you do that, then you're going to be able to see the boundary around the field. We've done this a few times. This is nothing new for you. I want to change a couple of things here. So one of them is going to be to change the color scale. I want to have a Viridis color scale. So let's go ahead, add a plus, scale underscore. So should I choose scale fill or scale color in this case? So
Okay, fill.
fill. Okay, so Amandeep and Polly said fill. And in this case is actually kind of interesting because so it is fill. So let's just go ahead and type that. But I want to tell you a little bit about why that's kind of interesting. So let's do fill Viridis B for bind, and I want option equals uppercase E. So the reason why it's kind of interesting here is that, so it is fill because on GeomeStars, it is implicit. It's not explicitly coded. It is implicit that it's filling GeomeStars with the one variable that it has, which is var1 pred, or the first variable in that GeomeStars, which is var1 pred. So it is doing the fill by that variable, which is our variable of interest, but it's doing that by default. We're not explicitly coding that, but it is fill. And if you change color here instead, if you were not sure and you changed color, you would realize that nothing would happen because you're not changing here the correct aesthetics. So scale fill Viridis, that's what we want to change. Also something else, I don't know if we discussed this much in previous classes. So here I use scale fill Viridis B for bind, and you can see that it creates bins. So the yellow bin is 53 and above, the kind of maroon type of, not maroon, I don't know what color this is, but a yellowish gray is between 51 and 53. So it creates these bins. If we would have used Viridis C, which stands for continuous, then we don't have bins, we just have a continuum, which impacts both the legend, but also how the data looks like. So just keep that in mind. You may want one or the other. It's just a style, like a design option. You're not changing the data, right? It's just, you're just changing the visualization of the data. So I want to keep B for bind. And then one more thing I want to do here is change the label of the legend. So we're going to use the function labs. And because we're changing the fill, so the legend represents the fill, then we say fill equals to, I want to call this 11.meters, like that. And then lastly, I want to apply my theme, which is an object we created in the beginning of the script. So my theme map is just gonna do this to our map. In a previous exercise, we also talked about the main map elements of title, legend, north arrow, and scale. Here we just have the legend. I'm not going to be adding all those elements, but if you do want to add them, you know how to do it. You can go back to that script that we added them. Okay, so this plot here should look familiar to you. You had a question on the exam that was exactly on this data. So it should look familiar to you that this field had, well, okay, so I think, let me ask this. Benedetta, can you help me to interpret this map here?
So basically the area more in the left are the one with the higher elevation,
Mm-hmm.
while toward the right we have a lower elevation.
Okay.
Yeah, the air points are specifically on the top, on the upper part of the field and the
Mm-hmm.
lower.
Perfect. Thank you, Benedetta. All right. So let me ask somebody else the following. Let me ask Amandeep. Amandeep, looking at the elevation data, where do you think water moves from and to? So tell me it moves from X to Y, like a direction.
So the elevation is more on the right side of the map.
Okay, lower on the right,
So water will move from left to right.
left to right? So it's gonna move this way. Yeah, perfect. All right, and we kind of saw that although in this interpolated elevation map, we don't really see those eroded fingers cutting across the field, but we know that they're there, and so that's also an indication for us to where water moves on this field. Okay, cool. So one thing to remind you is right now elevation is in raster format, is a stars object, and we need that to be able to calculate secondary terrain variables. So what do I mean? So primary terrain variable is only elevation. The reason for that is because this is the variable that's actually collected. The data is collected, that is collected on the field is elevation, right? So this is the primary layer. Now that we interpolated it, we're going to use this primary layer to calculate secondary variables that are going to be related to slope, aspect, flow direction, and there are some topographical indices we can also calculate here. So let's go ahead and do that. So the first one that we're going to do here is to calculate the slope of this field, which is going to be based on the elevation, right? So basically, well, I think let's go through this and then I'll tell you a little bit more about what is the slope and what it represents. So I left you here the object, I left you the starting data set, which is IDW-PRED, the raster elevation interpolated data. I'm selecting here only elevation, right? So if you just run this right now and you print slope, it's basically a stars object with one variable called LF meters. So here's the thing in R, and you may remember this from when we had a lecture. It's been a while since we had a lecture, but we were talking about different file types and also different packages that we use in R to handle geospatial data. For raster files, we had a couple of packages we talked about. So one was stars, the one that we're using, and there's another one called Terra. The package Terra is another package that also does raster operations in R. It uses a different object type. So even though the file is still raster, so it could be like a TIFF file. A raster could be a TIFF file. So the file is still the same on your computer, but the object in R is different for us to work with the package Terra. And the package Terra is the one that has the functions that we're going to need here to calculate slope, aspect, and others. Because of that, right now our object is a stars. We're going to have to transform that from stars to a Terra object and then calculate the slope. So that's what we're going to do next. So add a pipe here, come after that comment. The function that we're going to use, so I want to call the package name, which is Terra. Use the colon notation, and then it has a function called rest. So this function rest is what is going to transform our stars into a spat rest object, which is the type of object that the package Terra works with. So if you run this and you print slope, it's going to look different. So it's going to have even a different way of printing. So here it says it's class spat raster, its dimensions, It gives the extent or the bounding box, what's the CRS, what's the variable that we have, and what's the minimum and maximum values. So as you see, it prints differently than a stars object. It is a different type of object. It is a spat raster. So now that we have this as a spat raster object, now we can calculate slope. So add a pipe. We're gonna again call the package Terra. So Terra : and there is a function called terrain. So this function here, I do want to take a quick moment and do a help on this function. So help terrain. Let's take a quick moment to look at this function. There's a lot of things going on, but if we look at the description, so compute terrain characteristics from elevation data. The elevation value should be in the same unit as the map unit, so typically meters for projected raster data. So we're doing all that, we're good. And then what I want to show you here is this. So the V argument. So V argument can be one or more of these options: slope, aspect, TPI, TRI, Riley, TRI Ersmund, roughness, or flow direction. So these are all the things we can calculate from elevation data. And I want to show you here, if you come on the details, it's going to tell you more about how these are computed and what they mean. They give you here what is basically the formula they're using to calculate different things. So let's see here. So the TRI stands for, TRI stands for terrain ruggedness index. TPI is the topographic position index. And then it explains each one of the other ones. It provides you paper citations. So if you ever use these formulas here for an analysis that you publish in a paper, you may want to cite some of these methods here so people know exactly how your secondary terrain derivation happened. What was the theoretical basis of that? But anyways, I just wanted to show you here that V is the argument that you change to ask for what you want to calculate out of elevation. So here for us, our V is going to be equals to slope in this case. And I do want to change one more argument, which is the argument unit. So it's going to be either in degrees or radians when you're calculating slope and aspect. The default is degrees. I want the default to be, I want to change the default behavior to be radians. So let's say unit equals radians. All right. So if you go ahead and run that, and now you print this object called slope, it's pretty much still a spat raster, so it's not a stars yet. But now we have the values of slope. So these are in degrees radians. Before we do anything with that, I do want to do a couple of things here. The first one is going to be to bring this object back into a stars object. The main reason here is because we cannot plot spat raster objects with ggplot, but we can stars objects. So let's add a pipe. We're going to bring here, or we're going to transform this spat raster to stars by using the function st as stars. If you do that and you print it, I think our CRS is set, so I don't think we have to reset our CRS. And so the next thing here is I want to.
No.
Yes, somebody has a question?
No.
Just let me get my power cord because I just noticed I'm running out of battery. So now what happens here is to interpret a value in radian is a little bit difficult when we're trying to relate that to slope. So I want to transform that into a percentage instead. So a percent slope. So let's add a pipe, come here after the transform into PCT. Let's give it a mutate. I want to call this PCT for percent slope. And this is basically the tangent. So to call the tangent, we call a function called tan. So the tangent of the slope times 100. This is how we basically transform from radians to a percent slope. So if we run that and we print, now we have two values of slope, one in radians, one in percent. And now I just want to keep the percent one. I don't care for the radian one. So let's just go ahead and do a dplyr select and just get PCT. All right. So with that, I think we're done with calculating slope. Now our next step here is going to be to make a plot. I left you almost everything because almost everything is the same as before. I left you only one place for you to help me to figure out what we should do here. So we're starting with the ggplot. I have a geom ... What geom do we need here to plot the slope? What do you think, Luke?
Sorry about that. I was still checking the previous chunk. What was the question?
So I was just saying that, so we finished calculating slope and now we want to plot it. So I left all the code here except for the 3 dots right there. And I was asking, what is the geom we need to show slope?
Geom stars still.
Geom stars, right? Yes. Perfect. All right. So if you run that and then you create your plot, this is how it looks like. So we see that for the most part, our slope is higher on the top, on the top left of this field. And then, so here, the darker is the color, the lower is the slope. So we see lower slopes around here, and then higher slopes on the gray color, which is between 2 and 3, right? So really, we have slopes varying from, 1 to 7, perhaps. And this is the distribution of those slopes. All right, so one question that I get sometimes is what is a slope and how is it calculated? So basically for each cell, each pixel in this raster on the elevation raster, so let's go back to the elevation raster. So for each cell in the elevation raster, the algorithm basically, imagine that you are on top of one of the cells, and then you look at all of your neighboring cells. You find the neighboring cell that has the highest difference, the highest gradient from where you are. And that becomes the difference between, so let's say that I am on a cell that has elevation, let's say 53. And then I look at all my surrounding neighboring cells, and the one that has the highest difference from me, so I'm 53, and then I have a neighboring cell that is 51. That is the highest difference, assuming that's the highest difference like between all of my neighboring cells, then we basically calculate the distance from my cell to that lowest elevation cell of my neighboring ones divided by the area that each cell is covering. And that is just give you the slope between my cell and that cell. But it does that for all cells. So imagine that it moves from cell to cell doing this calculation. Moves to the next cell, looks at all the neighboring ones, see which one has the largest difference in elevation, uses that to calculate the slope between your cell and the neighboring cell. So that's basically what elevation is doing here. Or sorry, what slope is doing. So using elevation to calculate slope. right, so we just finished calculating the slope. Now my goal is to calculate aspects. If you compare the code between calculating slope and aspect, they're very, very similar, except for one difference. So we start with IDW-pred, which is the one that we have elevation interpolated as a stars object. We just select that var1pred, which is our value of elevation interpolated, rename it to 11 meters, transform that to a sped rest object, which is the type of object we need to work with the Terra package, which is where these functions are coming from to do the elevation and slope and aspects. What is the function that we're missing here?
Terrain.
Terrain, right? Yes. So Terra : terrain is the function we're using here. So what should be our V at this point if we want to do aspect? Aspect, right? So just say aspect right there. And then we want, in this case of the aspect, I want our units to be in degrees. And then everything else should be the same. If you just go ahead, oops, don't forget, like I forgot to add a pipe after that Terra terrain. Okay, so I think I may, oh, this is units singular, it's not plural. So then we have our aspect in degrees units. So it's ranging here from basically close to 0 all the way to close to 360. So the way that aspect, well, maybe let's plot it first and then we'll talk about the interpretation. All right, so on this data here, on this code to plot aspects, there's a few differences we need to fill in those 3 dots. I have here on the scale Filverides B, I added some very specific breaks on the scale, and I think it may help you in the near future to figure out why. But for now, just bear with me here with these breaks. The only thing you have to change in the code is the geom that we need to plot aspects. Kiathi, what do you think? What do we need here?
I think stars.
Stars, right?
Yeah.
Yeah, because aspect is stars object. So geom stars, let's just run that and take a look at this map. Okay, so what is this map here telling us? So this is basically, so if you take elevation and you calculate slope, you get a value of slope, right? Like this map. However, you don't really know which direction is that slope. So again, what happens is whenever the slope is being calculated, imagine you're sitting on top of one of the cells. You look at your neighboring cells and you compare your elevation where you are with the elevation of the neighboring cells. And then whichever neighboring cell has the largest difference in elevation from your cell, that then is the one used to calculate slope. The problem with that is that a slope map doesn't really tell you which neighboring cell was the highest difference. It could be the one right in front of me, it could be the one behind me, it could be the one to the left or the right. I don't know which one of my neighboring cells had the highest difference. I just get the slope based on that highest difference, but it's not telling me where in space that highest difference was. Aspect basically tells us that. So aspect here is a map that is showing in degrees which direction that slope is facing. So the way, imagine that you're sitting on top of a cell, and if you look north, if you look ahead, if you look forward, that is going to be your either 0 or 360 degrees. And as you're starting to make a circle around yourself, that is going from 0 all the way to 360 for a full circle around you or around the cell. So the aspect in degrees is just telling you which direct, assuming that if you're facing north, north is 0 and 360, right? Because 0, then you go all the way around, goes back to 360. 0 and 360 are immediately north. And then as you're changing the angle going around, facing your back, facing your right, facing your back, facing your left, coming back in front of you, that is the degrees that is being calculated as to which direction that highest slope is facing. So for example, we would see here on these cells in yellow, 337 is probably going to be somewhere like in this direction, sort of. So these cells are moving that direction, these yellow cells. The blue cells here are very, very low degrees. So it's kind of like going this direction. So if this is 0, 22 is going kind of this direction here, give or take, right? So that's where these cells are moving. So again, it just tells you, the slope by itself tells you what is the gradient between your cell and the neighboring cells, but it does not tell you what direction that gradient is. And aspect brings that information of where is that slope facing? Where is it going? Where is the highest slope based on your neighbors? So I do want to give you a quick moment here to ask if anyone has any questions, or maybe if you have, any observations about this. All right, so I don't hear anything. I'm gonna keep moving here. So I guess just one thing that we can think about here. So a degree of 67 would be moving directly straight to the east, right? So we see the 67 here is still towards the darker colors. So we see that a lot of cells are moving to the east, or the aspect is facing the east. Like the slope, the highest slope is facing east, which is again what we would anticipate based on what we know of this field. All right, so I want us to calculate one more metric here, which is going to be flow direction. So what is flow direction? Now that we know the elevation, we know the slope, so we know how much of a gradient there is in a given direction. And then with the aspect, we know what is the direction of the gradient, right? So now we know exactly how much of a gradient there is between neighboring cells and what is the direction of that gradient. Is it going east? Is it going west? Is it going north or south, right? So we have that idea when we combine both the slope and aspect. So combining slope and aspect gives you an idea of how much of a gradient there is and which direction that gradient is moving. With both of those pieces of information, we can calculate flow direction. So flow direction is going to be a metric that is going to help us understand where water or liquids would flow from and to in this field. That's what we're going to calculate next. So I left you here all the code already, except for the same components that we changed before. So let's see, is Mohit, what do you think? What do we need to change here to now calculate flow direction?
Terrain.
Terrain, right? So terra is the package, colon, terrain. All right, so our V now should be what? So the way that I would figure that out was coming here on the documentation, and I'm looking into this argument V and looking at the options, right? So we have options slope, aspect, TPI, TRI, roughness, and then flow dir. So flow dir is what we need here to calculate flow direction. And that's how I would determine what it would be called, is going to the documentation. So flow dir, I also want to have our units in radians in this case. Don't forget to add a pipe here at the end of the terrain. And then we're going to run this. Oh, again, I'm calling this units, it's just units, singular. All right, so now we have this flow direction, which has a minimum of 1, a maximum of 128. And we're going to talk about this in a brief second here. But basically, well, let's plot it first, and then I'll tell you how flow direction is calculated and how to interpret it. So again, we make a plot here. The only difference is now the breaks on the scale Fiborides are a little bit different, and I chose them by design. So we're going to realize why I chose those. So one thing we have to change in this code again is to call the appropriate geom here. That geom is geom stars, right? So we'll be using geom stars to plot all these products. All right, so if you run that and we make a plot, this is how our flow direction looks like, which is really very confusing if you don't know what these numbers mean. I want to invite you to come here on the documentation of the terrain function again. So if you're not seeing this, you can type help terrain and it's going to bring you to here. If you go on details, it has this part here under details saying flow direction returns the flow direction of water. That is the direction of the greatest drop in elevation or the smallest rise if all neighbors are higher. They are encoded as powers of 2. So power of 2 from 0 to 7. So a power of 0 to power of 7. The cell to the right of the focal cell is 1. And I guess instead of reading this, I'm just gonna ask you to look into this diagram here. So X is your cell, the cell that you are standing on. Imagine you're just standing on a cell. These directions here, so your cell is going to be coded with whichever number the water is flowing into. So for example, if I sit on a cell and then the algorithm behind the scenes is looking at both the slope and aspect to tell me how much of a drop there is and in which direction the drop is happening. So if the cell that you're in is coded as 1, then it means that water is flowing to the east, is going straight to the right. Imagine you are on top of the cell X, and then 1 is to the right, 16 is to the left, 64 is north, 4 is south, and so on. So this is, again, the code that we get here on this plot is just telling us what is the direction the water is flowing for your cell. So each time that this algorithm goes to a cell, looks at all the neighboring cells, determine where's the highest drop in direction, assigns a value to that cell that you are in based on this schematics here. Assuming that 64 is north and 4 is south, 1 is east, 16 is west. So, I don't know if I was clear enough, but we're going to test that right now. If you were to look into this plot here, and you can see the reason why I colored according to this very specific breaks is because those breaks match the classes that we get on the flow direction layer, which are these values. So if you were to look in this plot, I guess the first question I would have for you is which number here is majority?
128.
128, right? It looks like 128 is the majority, which are these yellow cells. If you had to translate these numbers into cardinal directions, like north, south, east, and west, what direction does 128 represent? East?
Northeast. Northeast.
Did you say southeast?
Northeast.
Northeast, right? Yes. So Amandeep said east. East would be 1. 128 is northeast, right? So all these yellow cells here, if water falls on those cells, it is moving northeast. That's basically what this map is telling us. It's saying, how is water moving on this field? To what direction is it moving? So I know it's like they could have done a better job of making this more intuitive, right? They could have, instead of giving us numbers like this, they could have given east, west, and so on. I wish they could have done that. But since they didn't, but they gave us this cheat sheet here to understand what direction matches with which number. That's how we would interpret this plot here. So similarly, let me ask somebody else. So we have a lot of yellows, which I'm assuming is going to be, 128 or between 64 and 128. But we also have a lot of dark blues here. So what direction is the dark blue signaling to us that water is moving into?
East.
East, right? Because 1 is right here. This is east, right? So all those dark cells are moving east. So either moving straight east or south, or I'm sorry, straight east or northeast, but moving east, which I guess is something that we were already hypothesizing that was the case once we looked into the elevation map, right? So we can look into this and already imagine the water is moving from the west to the east because of that elevation drop. All right. So I want to make a slightly different plot, which I think is going to help us to further understand flow direction. So if you come here on this next chunk, let's add a plus. Let me see, how can I explain to you what I want to do before actually doing it? I basically want to create a map where I can facet each one of these directions here. So imagine that instead of having all of these cells together, I want to have one map for each one of the cell types so we can clearly see which cells are moving into which direction. So let's come here on ggplot. We're gonna ask for geom stars because I want to plot this object, right? So geom stars. The data here is gonna be flow_dir. That's the name of the object. So flow_dir. And I do want to make a quick change on the go here, on the fly. I want to treat flow. So right now, flow_dir is a numerical variable. I want to treat that as a factor, but I want to do that kind of on the go here. So right here, after the data equals flow_dir, I'm going to add a pipe and I'm going to give a mutate. I'm going to say flow_dir equals to factor flow_dir. So this is basically transforming my flow_dir column into a factor, into a categorical variable rather than numerical. We're going to need that to do the facets. That's why we're doing this. If you just print or run that, this is how it looks like. It's just using a different color scale. I want to bring our boundary. So geom SF data equals boundary W. Fill equals NA. So it looks like this. It looks like our field. Let me see. I want to try to change the scale to scale underscore fill underscore Viridis D for discrete. And we've been using, let's see, we've been using option E. Let's just keep using the same option. So it looks like this. I want to apply our theme again. So it's called my theme map. My theme map. This is how it looks like. And now, because we transformed our column of flow direction into a factor, into a categorical variable, we can just go ahead and do a facet. So we can come here, add a plus. Let's call for facet underscore wrap. And I want to facet by flow there. If you run this, then this is what you get. Also, just to give us some more space, I want to remove this legend because we really don't need the legend. We have already the direction on the top of each one of the panels. So just to give us more space, I want to say theme legend position equals to none. So we remove the legend. So this is how this is going to look like for us. So really what's happening here is it's taking the cells that were classified into each one of those categories and then just plotting those cells by themselves and not mixing everything in one plot as we did the first time. So maybe this is going to help us to visualize better where are those cells going. I do want to make one quick change here because if you notice, it's kind of difficult to see the class 128 because of the color. That gray background is not really helping. So let me see how, let me try to remember how to change that. I think it would be maybe panel, background, element, rect, fill equals white. Let me see if that's the answer. Okay, yeah, that works. Okay, so this is how I changed the color of the background of the plot. I just use the panel background and then you call element rect for rectangle, element rectangle, and you say the fill equals white. Okay, so now I have a quiz for you. So let me pull out EOC and I'm gonna make that available. Mm. 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 Okay, so let me just make sure. Okay, so I just made it visible. I'm saving and closing. And then Luke, just give me a second for me to also make available for you. Okay, sorry, Luke, I'm still working on that on your side. So give me just a second here. Eva, can you set up a timer for 5 minutes, please? While I'm figuring this. Okay, look, I think it should be visible for you. And then I'm just gonna set a timer as well. Okay, so I'm gonna put 3 minutes to go. All right. Let's do this actually. So we can take a break after you take the quiz. So I'm just gonna reset the time for 5 minutes. So if you have answered already, go ahead and take a break. We're gonna take a 5 minute break. And if you have not, you can still work on that and then get a slightly shorter break after you finish if you wish. right, so let's resume here. Okay, so we basically just talked about the answers to this quiz, but any answer that would be either 1 or 128 is what I was looking for. This is the majority, right? One of these two is the majority. I think actually one, perhaps maybe the numerical majority, but 128 was close to that. So if you gave me any of those answers, you got it right. And then as we were just talking about, 1 would be your east direction, 128 would be your northeast direction. That's what I was looking for in that. Well, I guess any surprises? Did anyone think it was something else that you would like to share? Okay, good deal. So the reason why we were basically creating all these objects,
Dr. Leo,
yes.
I have a question. For creating the maps, for me, I got even the 0 and the NA. My maps also include 0.
Interesting.
Yeah, mine too.
Also mine, yes.
Mine as well.
Okay.
It's given in the help that if a point is 0, there are no points lower than that.
So you're getting basically a map here with 0, like another map
Yeah, before 1.
before 1. And
Yeah.
are there a lot of points there or what?
No, very few.
That's few.
Okay. Yeah, so as Kiati was saying, thanks Kiati for pointing that out. So if we were to come here on the documentation, at least, so for you, imagine that for you to have a flow direction, you have to have a gradient in one to one of the sides, right? So it explains at some part here that if you don't have a gradient with so right here, if the slope is 0, aspect is set to this formula. No, let's see, maybe not there. But there's a point here in the details that basically says if you don't have a slope in any given direction, then you may get a 0. Let's see. I guess I'm missing.
It's below the map given there in the help. They have given X and all the directions around it, right?
Or below this.
Yeah.
Okay, yeah, perfect.
It was below that.
Yeah, so if two cells have the same drop in elevation, a random cell is picked.
No,
No.
I don't see that in your on the screen, but I have that line here.
Ah,
It says cells without lower neighboring cells are encoded as 0.
okay, so I think what's going on here is probably that my version of the package is older than yours. So they may have made some changes since I updated my package. So I will probably have to update my package as well to make sure that we all have the same version. But yeah, so that's a thanks everyone for pointing this out. As you see on my side, I don't have that. And so I think in this case it's just because of a difference in package versioning and you having the most up-to-date version where they implemented this other step. But yeah, thanks for bringing that up. I mean, for our purposes, you don't have to worry about it, especially because it did not change our interpretation. So you don't have to worry about that. Just knowing that, you know, it's because of a difference in versions of the Terra package, most likely. All right, so we were basically creating those maps of elevation, slope, aspect, and flow direction individually, so we could bring them together in the end. If you remember, when we are adding a plus in between objects that both objects are ggplot, this plus here is actually not the same as a ggplot plus. This plus is coming from the package Patchwork, which is a package that we use to combine multiple plots in one. I highly recommend you look into the vignette of this package. So if you just type Patchwork R vignette on Google, you're gonna find their vignette. It's really, really helpful package to combine multiple figures. I've used this a lot for, combining figures for papers in the past. So this is what this plus is doing, is coming from that package. So basically we put elevation, slope, aspect, and flow direction all in one view. And then we just run that ggSave to export it to output. So we have this map on our output that includes elevation, slope, aspect, and flow direction. All right, so the next step here that I want to do with you all is, up until this point, elevation, slope, aspect, and flow direction are all raster. However, I do want to transform them to vector, because that's going to help us to visualize them, to visualize the data set better, and to understand the relationship between different data sets. To do that, we're going to first pull here. So we're going to first transform each one of these layers to vector, and then we're going to join all those vectors in the end. So let's begin here with elevation. I want to do this and assign it to an object called elev_v for vector. Give the assignment symbol. We're going to start off with IGWPred, which was that object that has the interpolated elevation as a stars object. We're going to use the function here sts_sf to transform from stars to SF, from raster to vector. We're going to change the arguments sPoints equals to false, and merge equals to false as well. If we run this and then you print it, we end up here with a SF object with 3,848 rows and 2 fields. Those 2 fields are var1pred and var1var. We already talked about those 2 fields. I just want to keep var1pred, which is the actual interpolation, and move on with that. Also, we have a geometry, because now it's an SF object. We have a geometry with that. And notice that this geometry is of type polygon. This is not a type point. So imagine that each cell that we had here is now, instead of a raster cell, it is a vector polygon. That's basically what we're doing with this ST as SF. So lastly, I just want to do a dplyr select, where I want to select the var1pred and rename that to elevation meters. So we can say elev_meters equals to var1.pred. If you run this, then we should have the following. So one thing for us to notice here is how many cells we have. So I have here 3,848 cells. You're going to have a different number of cells, because again, this comes back to the grid, which goes back to the boundary, which we all did individually. But let's see how this number is going to trickle down with the others and other variables here, and then be able to compare them. So for slope, we're going to do the same thing. So slope v, let's now transform slope from raster to vector. So we're going to start with the object called slope. If you just print slope by itself, it's that stars object that has that PCT in it. So we're going to do here an ST as SF. Same way we did before, we're going to say sPoints equals to false. If you don't change this, the default is sPoints equals to true. And then instead of getting polygons, you get points, which defeats the purpose. We just did interpolation because we wanted a continuous layer of, in this case now, polygons. If you get points, then you go back to the fact of having empty spaces. And then merge equals false as well. If we do that and we print it, we have PCT here. I just want to rename that PCT to slope. So let's give it a pipe. Let's call dplyr select. I want to call slope equals PCT. Okay, so we have, at least I'm going to compare my numbers, but you're going to see a similar pattern on your side as well. Elevation had 3,848 cells, and slope had about 300 fewer cells. Well, let's try to do this for aspect and see what happens there. So I left you the code for aspect. The only thing we're changing is the incoming data set, which we called it aspect. So just change that to aspect and run it. Let's see. So I got an error here saying that column values doesn't exist. I'm changing here to values. Let me see why. So if I run until right before that pipe, I actually get aspect already. So I don't even have to worry about that. That dplyr, I can just remove it. I think in a previous version of this package, the output here was calling values. And so that's why this was in place. So we don't need that anymore. You can just delete that and stop right there. And then lastly, with flow direction. So with flow direction, we're just going to change again here the incoming data set. This is flow dir. I'm guessing we're going to have a similar issue or a similar problem. So values doesn't exist. If I just run until right before the pipe, I already have flow dir right there. So I can just go ahead and delete this again. I think, again, this is just reminiscent of a previous script or previous version of this package. All right, so then we have our flow direction here as well. So kind of interesting is that we have here, so let's just look into the number of rows for a second. So elevation, we have 3,848. Then slope, we have 3,528. The same for aspect, and 3,839, which I think is even greater. Yeah, interestingly, is even greater than elevation itself. So what is happening here? Let me give you a visual assessment of what is happening here. If you go back to your output and terrain, you may have to squint a little bit to be able to see this. But look closely on the values of all four plots near the boundary. And tell me what you see. So the boundary has less points for all of the layers? Just slope?
But not flow direction.
So what's happening here is for slope and aspect, because it is basically like sitting in a cell, the algorithm is sitting in a cell and then is looking for all the neighbors to determine where is the slope and what direction that slope has. Every time that it did that for a value, so remember that's doing it on the elevation data, right? So every time it comes on the elevation data and that algorithm is sitting on a cell that is on the boundary, the default behavior of slope and aspect is because the cell is on the boundary, it does not have all neighbors around it, right? So it has neighbors to the east, but it does not have neighbors to the west. So the default behavior of the function is if you don't have all neighbors around you, you just assign that to an A. That's basically what's doing here. So elevation has all data, slope has missing data around the boundary because of that. The same with aspect. And quite frankly, I was expecting the same with flow direction. I think maybe there was a change in the way that they implement the flow direction algorithm that now it does fill in the gap, I guess. But that's why we have fewer cells in slope and aspect, because those are the cells near the boundary that don't have all neighbors around them. Okay, so now we took elevation, slope, aspect, flow direction, and we transformed all of them to SF, from stars to SF. And now our goal is going to be to basically join all these layers into one object that then we can export as our terrain object. So that's what we're going to do next. If you come on this chunk here, we're going to start off with elef_v, which is this object that we just created here, where we transformed elevation from stars to SF. So elef_v is elevation as a vector. We're going to start off with that. And then we're going to do a spatial join. I think we've done this before when we worked with the EO data. We use the function st_join for that. So here we give what is the next data. So our goal here, let me just take a step back. If you can imagine it, our goal is going to be to have one data frame with one column for elevation, one column for slope, one column for terrain, for flow direction, one column for aspect, and so on. In a way that a given row is the same cell in all maps. It just has different values for different terrain properties. So we're going to bring here now, we start with elevation, we're going to bring the slope. So slope v is the variable we want to bring in. If you remember, we've done this before, we have to change the join type. So the join is going to be equals to a function that the name of the function is st_equals. However, if you click here, it's going to give you the parentheses. You do not want the parentheses. Just have the name st_equals. Give it a comma. We're going to say left equals true. So by doing left equals true, what's going to happen here is it's going to start off with elevation, and it's going to bring slope with it. If you remember, the slope data frame here has about 300 fewer rows, right? We just checked that here, at least on my case. So again, just to refresh your mind, elevation on my side has 3,848, and then slope and aspect have 3,528. Because we're doing a left join, meaning that what's on the left is elevation, when it brings slope, all the cells that match in space are going to be matched. However, there are some cells in elevation that do not exist in slope because of those missing cells. We're still going to get an elevation point for them, but on the slope column, we're going to get an NA. So that's why doing the left join here, because what's on the left is elevation. All right, so if you do that, and you just run terrain v, we get elevation, we get slope, and notice how we have a lot of NAs right there from the beginning on slope. These are all the cells that we had data on the boundary for elevation, and we did not have data on the boundary for slope. If we get a summary here of terrain, we see that we have 320 NAs on slope, which is exactly the difference between number of rows on the elevation and on the slope objects. Does that make sense? Does anybody need a quick refresh here? All right, so we're basically going to repeat this step for the other two layers. So you can just copy the st join like that, just copy it, give it a pipe, hit return, paste it, and now we're just going to change the data set coming in. So on this second ST join, I want to bring aspect underscore V. And now on the last, so add a pipe, return, paste again. On the last one, we want to bring flow dir underscore V. Now, if you run all this and you print just terrain V, we have our 3,848 rows, which is the same number of rows as we had in elevation. And now we have the columns: elevation, slope, aspect, and flow direction. If we get a summary here, we see that we have 320 NAs in slope and aspect and 9 NAs in flow direction. These are the cells that were not able to be calculated because they were at the border. And again, I was expecting flow direction to have the same number of NAs as aspect and slope. It did not. I'm not quite sure why. But that's what we got. All right, so the last thing that I want to do on this exercise is just to export this layer. And the reason for that is at some point, we're going to bring back all these layers into the same script to do management zones. So now that we brought elevation, wrangled elevation, interpolated, used interpolated elevation to calculate slope, aspect, and flow direction, change all of them from stars to SF, merge them, and now export them. So let's call the function write underscore SF. We want to export this object terrain underscore V that we just created above. I want to export this to data. So // let's go into data. And I want to call this terrain underscore v.geojson. And always remember to change delete underscore dsn equals to true. So we don't, if you happen to run this code twice, it's not going to append, it's going to overwrite, which is we want to overwrite. So if you run this, you can go on your data folder and make sure that you have a terrain v.geojson there. And that should be it. So a quick summary here of what we did today. So we imported the point vector elevation data. We interpolated that elevation data. So we needed to have elevation interpolated as a raster so we could calculate secondary terrain variables. So we calculated those secondary variables of slope, aspect, and flow direction. Then we transform all of those 4 layers, including elevation and the secondary ones, into vector. We merge them, and then we export them as well, so we can use again. All right, so what is next then? So next, this coming Thursday, we're gonna do a soil electroconductivity exercise. We're gonna process that data. We're going to talk about it first, understand what it is, what are some of the methods that are used to collect this type of data, and then we're going to create a map of it. So we're going to wrangle, clean, we're going to interpolate, and then also export at the end, with the goal of at some point, we're going to have all these layers that were all interpolated to the same grid. So we can bring them back into one script and do management zone creation. All right, we're getting to the end here. I want to open attendance for you to claim. So let me just do that first, and then I'm going to open for any questions. All right, so make sure you claim your attendance. If you do not have any questions, then you're dismissed. But if you have any questions, I'm going to stick around for a couple of minutes to answer them.